So the method I was using to show and demonstrate chain rule in the previous videos is actually the way using Newton's methods of doing it, which is doing derivative of the outside times derivative of the inside. Leibniz's way was similar, but looked a bit different. I wanted you to at least see what Leibniz's method looked like. I will admit that most people seem to prefer Newton's way of doing things rather than the Leibniz way. But let's say we have a function, 3x squared plus 1, all raised to the fourth power. What Leibniz said is, he said, well, really, we have some function of u, where we have u raised to the fourth, and we just happen to have that u is equal to 3x squared plus 1. To make the connection to Leibniz, the u to the fourth is the outside, the 3x squared plus 1 is the inside. So then if we wanted to find the derivative of the outside, what we're really finding is df with respect to u, because our outside function is written in terms of u, that would be 4u to the third. Whereas if we wanted to find the derivative of the inside, that's u, the derivative of u, with respect to x, because this is written in terms of x, and that would be 6x. Well, the idea of this is similar to fractions, not quite the same, but what he said is df dx would be the same as doing the derivative of f with respect to u times the derivative of u with respect to x. And he said that we have to remember that df, du, dx are all very, very tiny changes in f, u, and x. And while looking at this, it looks like we can just go ahead and cancel the du's. We can get away with that, sort of. What we're really saying is that the du's are close enough that it's not going to hurt anything in our estimates to go ahead and cancel them because they're so infinitesimally small. They're not truly exactly the same because in df du, we actually control the size of the change in u because that's the independent variable. Whereas in du dx, we don't control the change in u, so it's probably a little bit different than the du that was with our derivative for f. And the reason we don't control the change in u on du dx is in that derivative, u is the dependent variable. So they're close, but not exactly the same. We can just kind of get away with it. So if we were thinking of it that way, I would have 4u to the third times 6x, which if I take the u and substitute 3x squared, would be 4 times 3x squared plus 1 to the third times 6x. And looking at this, we can see this is the same as using Newton's way. Here was the derivative of the outside. Here was the derivative of the inside. And then plugging in 1, so derivative of f with respect to x, such that x is 1. I can just plug 1 in for all the x's, so I'd have 4 times 4 to the third times 6, which would be 64 times 6. I'm sorry, not 64. Whoa, was I off there? It'd be 64 times 24. So whatever that value is what our derivative when x is 1 would equal.